Assalamu alaikum wa rahmatullahi wa barakatuh. This is the first lecture in chapter 3, the forces, al-Quwa. So the objectives of this class today is to know what is the meaning of the force, what is the effect of the force, to know some kind of forces like the gravitational force, and what is the difference between mass and weight, what the meaning of friction force, how to calculate the net force and the relation between the force and motion. We will study the last 2 points in the next lecture, but we will focus today on the gravitational and the friction forces. So starting with the force, what is the force? The force is the push or pull action upon an object resulting from the interaction of an object with another object. Like if there is a box and you try to push the box or try to pull it. Okay, so you are an object and the box is another object. So there is an interaction between you and the box. So you apply this action, which is a push or pull. So we say that you apply a force F, for example. Okay, what is the effect of the force? The force changes the status of the object. So if the object is in stationary, it might cause motion or acceleration to the object. If the object is moving, the force might be able to stop it. The force also can accelerate or decelerate the objects. Given a force, how to calculate corresponding motion? Using Newton's second law. Newton's second law is one of the most important laws in the classical mechanics. Newton's second law, it mentions a relation between force and acceleration. So the force equals mass times acceleration. And we will study it, inshallah, starting from next lecture. Okay. So this is how we get the relation between force and motion. Force equals mass and acceleration. And we will really use this equation, but very, very basically today. Allah, by his power, he has created 4 forces in the universe to keep the universe stable. These forces, according to our knowledge, is the gravitational force, the electromagnetic force, the nuclear force. And the nuclear force we can divide it into 2 types, the strong nuclear force and the weak nuclear force. In our curriculum, we're not going to study the nuclear or the electromagnetic forces. Okay, but we will focus on the classical gravitational force. So the gravitational force in classical mechanics. So what's the gravitational force? It's the attraction between any 2 masses in the universe. Any 2 masses, like 2 small stones, 2 rocks, 2 mountains, 2 planets, whatever these masses are, small or big. So any 2 masses, they have an attraction between each other. This attraction we call it gravitational force, قوة التجاذب. So this force depends on what? It depends on the mass of each object and also depends on the distance between objects. And to be more specific, distance between the centers of the 2 objects. Let's call this distance between the 2 centers, let's call it D. In some textbooks, they call it R. Okay, so it does not matter if you find it R or D. The most important is it's a distance between the centers of the 2 objects. So we can say the gravitational force, I will give it the symbol F sub G, or you can call it F only if you want, equals to what? Equals to a constant. This constant we will call it G, big G. Okay, so please don't get confused between the big G and the small g. The big G is only a constant, ثابت, and it equals to 6.67 times 10 to the power of negative 11. While the small g, usually we use the symbol G for the gravity acceleration. Gravity acceleration. So don't get confused between the 2 G's. Okay, the big G is a constant. The small g is a symbol for gravity field intensity or the gravity acceleration. Like on the Earth, on the surface of the Earth, the acceleration is 9.8 meter per second square. Okay, or Newton per kilogram, by the way, they are equivalent. Anyway, so let's go back to the force F. The force F equals a constant G, which is the universal gravitational constant. The universal gravitational constant. Or we can say the gravitational constant, it's 6.67 times 10 to negative 11. Times the first mass, the mass of the first object, times the second mass, the mass of the second object, divided by the distance squared. And please take care of the square, because many of you, while solving problems, forget the square of the distance. Okay, so this is the formula for the gravitational force. This gravitational force might be very, very small amount, like 10 to, let's say, negative 9 Newton. And sometimes it's very large. Sometimes it's very huge amount, like the force between the star and one of the planets, the sun and the earth, for example, or the earth and the moon. Okay, it's a huge amount of force. While if you have two stones or two small rocks, there is a force in between, but this force will be very, very, very small. Okay. If we have the earth, this is our earth, and let's say the radius of the earth is RE. This is the radius of the earth. And let's say the mass of the earth is ME. Okay. Let's assume that an object is here at the surface of the earth. Object. Let's call object mass small m. What is the gravitational force between this mass and the earth? What's the gravitational force? Let's try to do it ourselves. If G equals the constant G times the mass of the first object, which is the earth. So the mass of earth times the mass of the second object, which is a small object on the surface of the earth. I will call the mass small m, divided by distance in between square. What's the distance between the center of the earth and the center of the mass? The distance is almost the radius of earth. The radius of earth. As long as this mass is on the surface of the earth, so the radius or the distance is the radius of earth. Okay, so divided by RE square. Okay, let me do it in red color so it will be the same one. Okay, so this is a formula for the gravitational constant for an object at the surface of the earth. There is another name for this gravitational force. I can call it the weight, الوزن. Okay, so this gravitational force at the surface of the earth, we can call it the weight of the object. How to get the gravity acceleration G, the small g? I know that Newton's second law says what? Force equals mass times acceleration. Force equals mass times acceleration. We just wrote it 5 minutes ago. So if I'm thinking about the gravitational force, if G equals the mass times the gravity acceleration, and I can say the gravity acceleration is G instead of A. So if you want to get G, you need to divide the gravitational force over m. You need to divide the gravitational force over the mass of the object. The mass of the object, which is this object. Okay. So if you want to get the acceleration over this object, you need to divide Fg over the mass of the object. So I can say G, which is the gravity acceleration or the gravitational field, equals G equals, excuse me, the gravitational force divided by the mass of the object. So you need to divide this formula, you need to divide it over the mass of the object. When you divide it over the mass of the object, easily you can remove this m with this m. So the leftover becomes what? G times mass of the Earth divided by the radius of the Earth square. So this is the formula for the gravity acceleration or the gravitational field, okay, which you can find it here. So again, we have two formulas now. The formula for the gravitational force, or we can say it here on the planet, we can say it's the weight of the object, and the gravity acceleration or the gravitational field is this gravitational force divided by the mass. The difference in between is just the mass of the object, the mass of the object. Because you know, if you want to get Fg, you just multiply the mass times the gravity acceleration. In many cases, instead of writing Fg, we can write weight. So instead of writing Fg, the gravitational force, we can write it the weight, as long as we are talking about the gravitational force on an object at the surface of a planet. Okay. So, by the way, if there is, like, let's say you can climb over a mountain. If there is a mountain here, if there is a mountain, and we take this object to the top of the mountain. So instead of being at the surface, no, I will take it here to this point. And this mountain is at a height h. So how to calculate the gravity acceleration and the gravitational force? The gravitational force Fg will be the big G times the mass of the Earth times the mass of the object divided by what? Divided by the distance squared. The distance here is not the radius, but it's the radius RE plus the height h. So the distance now is this total distance. Let's call it d. It's RE plus h. So I can say it's divided by RE plus h total square. Okay, so this is if you are at a certain height from the surface. What about the gravity acceleration at this position? The gravity acceleration equals Fg divided by m, which is g times me divided by the distance re plus h total square. Okay, so this is a formula. Okay, you don't need to memorize it. As long as you memorize the basic formula, this one and this one, so you can get the gravity force or the gravitational force and the gravity field or the gravity acceleration, sorry, at any point. Okay, so these are the formulas here. You can look at it. Okay, the last formula says what? The weight equals mass times gravity. So we need to understand what's the difference between mass and weight. Mass is the quantity or the amount of matter in the object, and it's measured in kilogram. It's measured in kilogram. Like if you have a bottle that has some liquid, like a bottle of water, let's say the bottle has half kilogram of water or half liter. Okay, you know that the density of water is 1, so half liter is a volume, and it's equivalent to half kilogram if you change it into a mass. Anyway, so if you have half kilogram of water and you tighten and you close the bottle, so it will not leak outside. So if you take this bottle to the desert, if you take it to a mountain, if you take it to the ocean, it doesn't matter. Wherever you go, it stays the same mass, which is 0.5 kilogram. Okay, if you take it to the moon, if you take it to the free space, if you take it to Mars, it doesn't matter. So the mass stays not changed, while the weight depends on the gravity. The weight depends on gravity acceleration. So it depends on where you are. If you measure the weight at the surface of the Earth, it's different from the weight if you are at the top of the mountain. It's different from weight if you are in an aeroplane or at a certain orbit around the Earth. It's different from if you measure it at the moon surface or on Mars surface or free space. So the weight depends on the gravity acceleration. The gravity acceleration here on the Earth is 9.8. Almost, it's on average 9.8, sometimes a little bit more or less. Okay. On the, let's say on Mars, the weight will be the mass times 3 point something, I think 3.3 or 2, something like that. On the moon, it's the mass times around 1.6 or 1.6 something. Okay, so the gravity, if you are in the free space, it might be the mass times, let's say, zero point 0.2 or zero point 0.1 or maybe less than that if you are away from the gravitational fields. Okay, so the weight depends on the gravity. Two elephants, each of mass 2,000 kilogram, attract each other gravitationally because they are two masses. So they attract each other. But because they are small masses, they are not planets, they are not stars. But still there is a gravitational force. But this force will be very, very small force. So they attract each other gravitationally with a force 2 times 10 to the power of negative 5 Newton. So this is a small force. How far apart are they? We need to know the distance between those two elephants. So if I have an elephant, I don't know where is head. Okay. Two elephants here. Let's say this is the center of the bodies. So the distance in between is d, and they attract each other with a force 2 times 10 to negative 5. The mass of the first one is 2,000 kilogram. The second one also 2,000 kilogram. I need to find the distance. So I will use the gravitational force equation. If G equals the constant G times the first mass, let's call it MA and B, times MB divided by the distance square. So I know if G is 2 times 10 to negative 5 equals G is 6.67 times 10 to negative 11 times the first mass 2,000 kilogram, second mass 2,000 kilogram, divided by the distance square. So we need to solve this simple equation to find the distance. I will take the distance to the left-hand side, take this force to the denominator on the other side. So the distance square is 6.67 times 10 to negative 11 times the 2,000 times the other 2,000 divided by 2 times 10 to negative 5. So this gives you d square. D square. If you want d only, so you need to take the root of the whole number, and this will give you at the end around 3.65. Again, we use a decimal point, not a comma. So please don't write it 3.65 like this. This is a mistake. Okay, don't do that. So it's a 3 point. You have to use the point. Okay, 3.65 meter. Okay, guys. So this is the distance between the two elephants. Two objects attract each other with a gravitational force of a magnitude 1 times 10 to negative 8 Newton when separated by 0.2 meters. So it looks like similar to the previous one. If the mass of one of them is 2 kilogram, of course you will ask about the second mass. What's the mass of the other object? So we have two objects, 2 kilogram. The other one is not known. I will call it MB if this is A. The distance between them, of course, the distance between the centers is 0.2 meter, and the force of attraction is 1 times 10 to the power of negative 8. So I will use the same equation. If G equals big G times the first mass times second mass divided by the distance square, I know the force is 1 times 10 to 8. G is 6.67 times 10 to negative 11. First mass is 2 kilograms. Second mass is M sub B, divided by the distance square, which is 0.2 square. So don't forget the square. So 0.2 square is 0.04. Okay. Then let's try solving, excuse me. Let's try solving the problem to find MB. So MB will be what? Take this 0.4 to the numerator here, the other numbers to the denominator on the other side. So it will be 1 times 10 to negative 8 times 0.04 dividing by 6.67 times 10 to negative 11 times 2, right? Okay, so the result will be around 2.999 something, which is almost like 3 kilogram. So almost you will find it 3 kilogram. The planet Dune has a diameter. It's a fake planet. That's like an imaginary name. I don't think there is a name like this. The planet Dune has a diameter. Do you know what's the diameter? Al-Qutr. Diameter, like this is the diameter, and the diameter equals 2 times radius. Okay, you know that. So this is the diameter, and the small one, or half of it, is the radius. So there is a planet Dawn, its diameter is 8 times that of the Earth. So the diameter of Dawn equals 8 times the diameter of Earth. So what's the relation between the radii? The radius, I can say also the radius of Dawn equals 8 times the radius of Earth. It will be the same relation. Like divide both of them over 2, it will give you the radius. So it will be the same relation. 2 goes with 2. Okay, guys? Also, the mass of Dawn is twice. Twice means 2. Twice as large. So also I have another relation. The mass of Dawn equals 2 times the mass of Earth. If there is a robot, its weight is 1800 Newton. So the robot weighs 1800 Newton. So this is the weight of the robot. 1800 Newton. But where is this? Is it on the Earth? No. It's on the surface of Dawn. On the surface of Dawn. So let me call it WD. The weight of the robot on the surface of Dawn. What will be the weight of the robot at the surface of the Earth? So I need to find the weight at the Earth. I know that the weight at the Earth is mass times gravity, our gravity, and our gravity is 9.8. Okay, but here I don't know the mass. I don't know the mass. So what shall I do? There are more than one solution or one way to the solution, and all of them, they have the same idea. I would say what? I can say the weight at Dawn, which is 1800, equals the mass of the object times the gravity of Dawn. Okay, and the weight on the Earth equals the mass of the object times our gravity, which is the 9.8. I will call it G only. Okay, I will call it G. So G is the gravity acceleration or the gravity field on the Earth. I know it 9.8. GD, this is the gravity of Dawn, which I don't know what is it. Okay. The mass is constant. I said that 5 minutes ago. The mass does not change. So I can say, okay, the mass equals 1800 Newton divided by GD. And also the mass equals the weight of the object divided by G. So I can equate both of them. Like I can make a relation between the Dawn and the Earth. So I would say the 1800 divided by GD equals the weight on the Earth divided by our G. Okay, that's relation. I know this G is 9.8. So if we can find the other g, or a relation between the gravity and the other gravity, so we can get the weight on the Earth. How can we do that? There is a relation, if you remember, the gravity at dawn equals the big G, the constant, times the mass, the mass of the planet dawn, divided by the radius of dawn square. Okay, this is the formula for the gravity acceleration of dawn. We can rewrite it as what? The mass of dawn is what? Is twice the mass of Earth. And the radius of dawn is 8 times the radius of Earth. But take care that it's total square. And if you are going to square it, so this is equal to what? 64 times RE square. So I will remove it and write it down as 64 times RE square. Okay. Let's simplify it. Divide over 2, divide over 64, it will be 32. Let's take the 32 outside. It will be 1 over 32 times what? Times g times the mass me divided by the radius re square. What is this part in the circle here? This is the formula for our gravity, because this is the mass of Earth and this is the radius of Earth. So this is a formula for our gravity. So I can say that there is a relation between GD and our gravity. GD equals 1 over 32 times our G. Or you can write it here, G over 32. Of course, you know that G is 9.8, so you can substitute if you want. Or you can take it directly and substitute it here. Okay, so let's take this relation again. Let's take it and write it again. 1800 divided by GD, which is G over 32, equals W over G. Okay. Now you can, instead of substituting the G equals 9.8, we can remove this G with this G. Like, instead of substituting, to remove them together, it's easier. And this 32, it's in the denominator of denominator, so you can take it up. Okay. So at the end, W equals to what? Equals to 1800 times 32, of course, times 1 divided by 1. If you want to make like the method like you used to make it, you can call it scissor or whatever. Okay. So at the end, please do it yourself. You will find it 1800 times 32. That's 57,600 Newton. So this is the weight of the object on the Earth. So as you can see here, the acceleration of the Earth is much, much higher than the acceleration of dawn. So although dawn is bigger, but bigger doesn't mean it has higher gravity. It does not mean it has higher gravity, because the gravity depends on two factors. It depends on the mass and the radius. The mass and radius. So the more the radius, the lower the gravity, especially that it's squared. Okay, and the more the mass, the more the gravity. So the more the radius, the less, sorry, the more the radius, the less the gravity. Okay, because it's square, and the more the mass, the more the gravity. Rank in order. Okay, so we need to put them in order from largest to smallest. What is it? The gravitational field, the G, the gravity acceleration. So the gravitational strength on the surface of the following planets. I will divide them and try to find G for each one. So G1 equals the constant times the mass. The mass here is M, divided by the radius here is R. square. So this is a formula for the first one. The second one, G2, or 2 in Roman numerics, equals the constant times the mass here is 2 times m, so it's 2m, divided by the radius squared. The radius is r, so it's r squared. So I will take the 2 outside, 2 times g times m over r squared. So this is G2. This is the formula. The third one, G3, equals the constant times the mass, which is here m, divided by 2r total square, because the radius here is 2r. So what's 2r total square? It will be 4 times r square. So we can write it 4 times r square. Take this 4 out. So it's 1 over 4 times g times m divided by r square. The last one, G4, equals the constant g times the mass is 2 times m, so it's 2m, divided by the radius square, similar to the previous, so it will be 4 times r square. Then simplify it, 4 over 2 is 2, so and here is 1, so it will be 1 over 2 times g times m divided by r square. Okay, guys? So how to compare which one is the largest one? The one that has the 2 here, so this is the largest. This is number, let's call it A. Then what is the second? This is the second, B. Where is the third? The one with half. So this is the third, let's call it C. And the last one is the 1 over 4, so I will call it D. So this is how we rank them from largest to smallest. The International Space Station orbits Earth at an altitude h equals RE over 16. So the International Space Station, محطة الفضاء الدولية, it orbits the Earth, moves around the Earth, okay, at an orbit which has an altitude or a height from the surface h. This h equals what? Equals RE over 16. Okay, what's RE? RE is the radius of Earth. Okay. What is the weight of 100 kilogram astronaut? Astronaut means رائد فضاء. Okay. What is the weight of 100 kilogram astronaut inside this station? So if there is an astronaut here inside the station and his mass is 100 kilogram. So how to calculate his weight right there? So the weight, I know, equals mass times gravity, but the gravity there is not 9.8. It will be less than 9.8 because you move away from the center of Earth. Okay, so you increase the distance between the center and yourself. So this G, I will call it GS, G station, the gravity at the station, which I know that it's lower than 9.8, believe that. Okay. We need to find this GS. Let's write down the formula. GS equals the constant times the mass of Earth divided by the distance square. It's not here the radius of Earth because the distance, here you call it R, but it's better to call it D, okay, because R usually it's a radius. Okay, let's call it D. This is the distance between the center of Earth and the space station, which is what? It's the sum of two distances, the radius of Earth plus the h, which is RE over 16. So I will remove this D and write it down as RE plus h, which is RE over 16, total square. Total square. So again, if you know that RE plus RE over 16 equals, this RE means 16 over 16 RE. 16 over 16, okay? So it will be 17 over 16 times RE. So RE plus RE over 16 equals 17 over 16. So it's G times mass of Earth divided by 17 over 16 times RE total square. So we can distribute the square to both of them. So this 17 over 16 square, and the RE also is squared. What's 17 over 16 square? 17 over 16 total square, it's around 1.129. Okay, so again, this can be written as G times the mass of Earth divided by 1.129 times RE square. You can take this number out here, 1 over 1.129. It's a little bit better. Okay. Okay, so that's much better. Then look at this part of the formula. What is this? What's this? We saw it before. This is the gravity acceleration at the surface or on the surface of the Earth. This is the 9.8 actually. This is our G. This is our G. So you can say the gravity at the station equals G divided by 1.129. Or you can say it's 9.8 divided by 1.129. So now I can substitute here in W. And this W is not the normal W. This is also WS. Let's call it WS, the weight of the object at the station. This is not on the surface of Earth. So the weight of the object or the astronaut at the station equals its mass, which is 100 kilogram, times what? Times G, which is 9.8, divided by the 1.129. Of course, it will give you, or this result is less than 9.8. So the result will be around 868 Newton, around this number, 868 Newton. Okay, guys, the mechanical forces. Uh, we will deal with four kind of forces in the classical mechanics problems. If you are pushing or pulling a box, so you apply a force on this box. Your force, we call it external force. External force. A force comes from outside, like if you push by yourself or you use a machine to push or pull or lift something. Usually we call these forces external forces. Okay? It's the action or the force of push or pull. And sometimes it's horizontal, sometimes it has an angle, sometimes it's like this. It doesn't matter. It depends on how do you apply your force. The second force is the gravitational force, or as we will say it, the weight. We are not going to use this word gravitational force again, but for the motion of objects, we will use the word weight. Okay, so weight W equals what? Equals mass times gravity, and its direction is always downward. Downward. Okay, so if I give you, for example, an incline at 30 degree. Incline means سطح مائل. An incline like this one. And there is an object on the incline. And I ask you to draw the direction of the weight. So some people actually, they draw it like this. And they say W equals mass times gravity. This is a mistake, a big mistake. Okay? Because the direction of the weight is downward. Okay? So please don't get confused. Okay? Downward, like this one. So this is the second force, the force of gravity or the weight. W equals mass times gravity, and the gravity is 9.8. The third force is, we call it the normal force. Normal here, the word normal here means عمودي. عمودي. Okay? So the normal force, it's normal or perpendicular. Perpendicular also means عمودي, perpendicular. Perpendicular to what? It's perpendicular to the surface. Perpendicular to the surface means it has 90 degrees with the surface. 90 degree with the surface. We call it the normal force. And also it has another name. Sometimes we call it the normal, excuse me, the normal reaction, the normal reaction. When you study, inshallah, engineering mechanics, we will call it the normal reaction. Okay. So this is the normal force or the normal reaction to the surface. So if there is a wall, for example, or here, let's say in this case first, where is the direction of the normal force? The normal force is perpendicular to the surface. Perpendicular to the surface, so 90-degree with the surface. This is N. Let's say there is a wall. There is a wall. Okay. And let's say there is a small object. Let's say you are here and there is a small object that you try to push against the wall. You try to push this object against the wall. Okay. So the wall produces a normal force. This normal force is perpendicular to the surface. Okay. So this is also the normal force of the wall. Okay. The last one is called the friction force. Friction force. قوة الاحتكاك. What is a friction force? Friction force is a kind of resistance, okay, that the wall or the surface produces, and it's against the motion. This force is a resistance against the motion. So if the motion is to the right, this force must be to the left. Okay. So this is the friction force. So what's the meaning of friction force? If you look at any surface like the teapot here, it might look like it's shiny or polished. But actually, if you look under a microscope or if you use a magnifying glass to look deeply to the surface, you will find bumps, you will find dents, you will find irregularities on this surface. Okay, so if there is a surface like this one between two objects, object A and object B, if we look deeply at this surface with a magnifying glass, for example, we will see a lot of irregularities, a lot of irregularities. These irregularities, we call it the roughness, al-khushuna. Okay, sometimes it's very large, sometimes it's very small, but usually you cannot finish it perfectly. Like it looks like sometimes it's smooth, but under the microscope there is nothing called smooth. Under the microscope there is a roughness, but this roughness might be a high roughness or low roughness. Okay, there is these irregularities, the irregularity of the lower surface and the irregularities or bumps of the upper surface. Because they are pushed against each other, so these irregularities, they cause resistance. So if you try to move the first object to the right relative to the second object, because of these irregularities, there will be a resistance. This resistance is called the friction force. This resistance is called the friction force. If there is a lot of irregularities and big irregularities and hard irregularities or hard and solid pumps, there will be a lot of resistance. So the friction force will increase. And in general, in physics, we call it the roughness of the surface. So if you increase the roughness of the surface, the friction force will increase. What else? Also, if you push the two objects against each other, like if you push them with a force against each other, this will increase the friction force. Why is that? Why if you push them against each other, this will increase the friction force? Because you allow those irregularities to enter and be closer to each other more and more. Okay, you push them against each other, so this will increase the resistance. Okay, because you bring them closer to each other. You allow them to allow these irregularities to enter inside each other. Okay, so this will increase the whole friction force of the surface. Okay, this is what we say here. As you see here also, this a picture of a tile under the microscope. It looks shiny. Here it looks smooth, but under a microscope it's not. Okay. There are two types of the friction force. Two types of the friction force. One of them is called the static friction. Another one, we call it the sliding friction, or in mechanics, we call it kinetic friction. Kinetic means حركي, something related to the motion. Okay, sliding means انزلاق. So there are two types, the static and the sliding. What are they? Let's say there is a box or a table or whatever, and you try to push. You are here. Okay, you are trying to push this box or this table. Uh, Maybe you will not be able. Like, let's assume that you are trying to push it, you are applying a force F, but you cannot move it. Why is that? Because there is a resistance. There is a resistance, okay, opposing the motion. Opposing the motion. This resistance is a friction force, but the object does not move. In this case, we call it the static friction. We call it static friction. So what is the static friction? It's the friction force when the object is at rest. Okay? The object is still at rest. You try to move it, you apply force, but you cannot move the object. So the friction in this case, we call it the static friction. What if you are stronger? So you are able to move the object. So the object can slide. So the object will move. Does this mean the friction is zero? No. There is also a friction. If you push an object and the object is moving, and you can try it yourself at home, you will feel still some resistance. You will feel some resistance, but not as much resistance as before. Okay? This resistance is also friction force of the surface, but this is while sliding or while moving, so we call it the kinetic friction or the sliding friction. So the sliding or the kinetic friction is the friction force while the object slides on the surface. As a property, خاصية, for the surface, the static friction is greater than the kinetic friction. So the static friction is always greater than the sliding or the kinetic friction. Okay, guys? So that's everything today. Thank you for watching this lecture. I will see you next time, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.